Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'm pleased to introduce Geoffrey Fox. Geoffrey Fox is visiting Microsoft Monday through Thursday of this week, and he's giving the third lecture in a series of 4 lectures on the history of high-performance computing. And with that, I'll turn it over to Geoffrey to continue from where he left off yesterday.
Okay. So we're continuing my homework set, which was to establish the Microsoft Foundation classes to solve the Intel application framework. And last time we discussed Kmeans. And so we will continue with frequent Itemset mining and support vector machines. So before I get on to the new topics, I will just note that K-means is just one of many algorithms which are of the same general class, and you can make it, you can refine these algorithms in various ways. Many years ago, I wrote several papers on how you took K-means and made them more sophisticated using so-called multi-scale methods. The problem with K-means is one of these greedy optimization algorithms that often finds local minima, and there are various strategies to avoid that, one of which is called annealing. And a way of annealing in K-means is to basically anneal in the distance scale in the space where you're doing the clustering. Because if you start off with no resolution and look at the whole world, there is only one solution because everything's at the same point. And you can decrease you can change K-means to a model where you gradually decrease the increase the resolution and look at finer and finer scales, but by tracking it to the one at the coarser scale, you avoid getting trapped in local minima. This is what is the foundation of simulated annealing as an optimization method. Here, the temperature just corresponds to the distance scale. So there's a whole set of papers done by my student at Caltech, Ken Rose, and you can find them if you go to Google. And they just do all these usual physics things of assigning probabilities to a point belonging to a cluster. And the energy function is just the same thing as the ordinary K-means energy function. Is just the sum of the squares of the distances from the points to the cluster centers. And you can for a given distance scale, you can solve these problems, and you can find the solution for the centers as a function of the distance scale, which is the temperature. And as far as this talk is concerned, the only point to be made is that this paralyzes in exactly the same way as the ordinary K-means, because the only thing you're doing here, which is computationally intense, is summing over points and centers the mean square distances, and that can be calculated in parallel just as well as anything else. And so this just again points out that parallel computing is not particularly sensitive to how hard the problem is.
So for this problem, what's the dimensionality, information dimensionality?
It's the same as before, 1. And so we claim this gives better answers than the K-means method, and this is the standard diagram to show why annealing avoids local minima. If you use the K-means, you would look at this top graph. You have these bumpy minima curves, and you're liable to get trapped in a local minima because you always go to the nearest minima with K-means. If you do annealing, you hope to track. Yes, this is very coarse distance scale when you're bound to get the right answer, and then you hopefully track. So this is.
So in this method, you can start with any arbitrary initialization.
That's right. Yeah. Well, you start at the coarse resolution when the answer is trivial, because it's just the total centroid of everything. Or there's only one cluster. Everything is at the same point.
Well, actually, I know that a lot of techniques have been developed of initializing the cluster intelligently so that the standard is...
So here we're initializing it by annealing in distance scale. Because at the coarse distance scale, you actually, your cluster at the right, if you choose a scale actually equal to the cluster size, the centers are just all you see.
So you're saying all annealing techniques, Kmeans or otherwise,
annealing usually always paralyzes because there's Monte Carlo, and they typically are done with these types of energy functions. These energy functions are almost always evaluatable in parallel.
So are there libraries available for all these standard algorithms which are easily parallelizable?
Well, there are many libraries. Whether they are actually tweaked to the problem, I doubt if there is for this problem.
So it would be nice to have that kind of library set up.
Well, as I said, slightly superficially at the beginning, if you believe in the Intel application suite, they have a clear description of what libraries you need, do you not? And so one could, if one wanted, sit down as a nation or as a company or as a university and build that application suite. Because I would claim they all, I mean, as far as I know, all the hard Intel algorithms run in parallel.
Okay, so once they come up with their multi-core CPU, for instance, then the developer is able to directly call the library they developed.
That's right, yes.
And then at whatever language.
As we said, one of the standard approaches to parallel computing is the Marine Corps approach, where the Marine Corps builds the libraries and the user incorporates the libraries in their code. That is what Department of Energy uses, and it's a very good technique. And it avoids a lot of the difficulties with the other approaches to parallel computing of trying to make it easy.
So in that case, the users can simply use high-level language like C++ to call those routines, so that they can spread out. Or does it require some different
this is a little probably.
Things much easier, more intuitive than using sequential language.
Well, we can come back and discuss this later. But if you think about, I mentioned before that problems consist of components, and those are. I mean, I think the general problem is a meta problem. It has lots of parts, and usually what one wants to do is to parallelize the parts. That's what the Marine Corps does, and then what the user does is program the workflow that joins these parts together, which workflow is not itself going to run with it will be running with loosely coupled parallelism, and it's not difficult. I mean, then we have workflow and mashups as the technology to support it, and I would claim that is straightforward technology. I have some, if we ever get to my cosmic slides on parallel computing software, it is discussed in those slides.
So it doesn't require any new type of programming language. The standard programming language can call it.
Let's just go on.
Those are all important questions, and it's very important to decide if you. Historically, we always thought we wanted a new programming language, and I started this project with Ken Kennedy, called the Center for Research in Parallel Computing in 1988, to develop these new approaches. People still use the same approach they did in 1987, and do not use any of the new languages, because the new languages, although they had some advantages, were not as general and as easy to predict the performance of as the old, rather more humdrum approaches. So, blah, blah. So, I've said everything. As always, these techniques are not generally known, and I work in chemical informatics. It's interesting that whole field does not know about these types of multi-scale algorithms, but so that's a different point. All right, so now we have the next Intel problem, frequent item set mining. And here the problem is the following. You have a database with records. The records has items in it, which has each record is a vector of items. The items come from some source vocabulary. And you want to find item sets that occur frequently, which are subvectors which occur in lots and lots of records. Presumably, if this was a set of purchases from Walmart, these would be the items would be cans of fruit and things like that, and you want to find which correlated sets of items people purchase. And there is multiple algorithms for this on sequential machines, and two I looked at for this homework are called a priori and frequent pattern growth. And the a priori is the simplest sort of combinatorial search method. You start with the smallest item sets, namely one item. You count the number of times each item occurs on its own, and then you just increase from 1 to 2 to 3 and so on. And it is impractical to find very large item sets in that fashion. And there's another one called frequent pattern growth, which rather than focusing on the item sets, focuses on the records or the transactions and reorders them and looks from patterns inside the transactions. And it effectively regenerates a new database.
So one question. Are you talking about, you say records are a set of items, are you talking about subset equality? I mean, because your item sets could be defined in several different ways. Your notion of
remember, I'm just doing this as a homework set. So I go to Google and Wikipedia and look all these things up. I did read several papers which were published on this, and so as far as I understand it, the items are, like I said, for Walmart. They come from a vocabulary, which would be the Walmart inventory. And you're looking at the order does not matter. You're asking how often a set, an unordered set of items occurs in the record.
Okay.
That's the problem as stated. Obviously, there are many variations of this problem.
Is also bot problem.
Yeah.
And now we look at paralyzation. And both methods there is a discussion of paralyzation. As far as I know, didn't look as though it had been used much, if at all. And the way you paralyze this is data parallelism over the database. At least that's the way these people paralyze, which seems natural. You just take the database, divide it into parts, and you count the patterns in each subset of the database. Then you need to accumulate the total item set counts, and that is actually identical to the problem we just did with Kmeans of doing a global reduction. And so this algorithm is straightforward to parallelize. It is particularly efficient on multi-core machines because in order to do here, unlike the clustering algorithm, the global reduction we were doing MPI or reduce for only had a few things we were reducing. In this case, the centroids of the clusters. In this case, we're reducing every single item set, which could be a large number. Therefore, the efficiency of that global sums is quite important. It can be optimized by noticing you do not have to add up item sets that don't occur very often, but quite how you do that is not so trivial, and it was not discussed in the papers. On multi-core, it's particularly trivial because we can do this transposed algorithm I mentioned last time. So here we have 4 processors. It's adding up, in this case here, it's adding up the occurrences of item sets in the 4 parts of a database, and it gives you a vector. The 4 represents processor 4, and I've only taken four patterns here, and it just tells you the count as far as processor is concerned of patterns 1 through 4. In order to add up the total counts for pattern 1, we need to just sum the numbers produced by processors 1, 2, 3, 4. And so to do that on a multi-core machine, because it has a shared memory, we just have to transpose. We have to change the decomposition, and instead of decomposing over database, we decompose over item sets. And we assign equal numbers of item sets to each processor and do these global sums. That way we do not have the logarithmic term that you get with on a distributed machine when you do the summation. That's again a typical strategy. You often have to change decompositions and do transpositions to make it more efficient. Fast Fourier transform is a well-known example of a standard parallel algorithm where you transpose to bring the butterfly algorithm into memory, and that gives you a significantly more efficient algorithm than doing the FFT in a distributed fashion. So this algorithm looks particularly good on multi-core machines.
So if I understand this right, you're just relying on the fact that on a multi-core machine, the memory is really close to the
I'm just using a shared. When I say multi-core, I can say shared memory.
Shared memory. So NUMA machines would still be a problem.
Yes.
Okay.
Yeah, all the 1,000-core processors are NUMA.
Right.
And even on multi-core machines, you're basically going to run at the speed that you can.
All of these things are sensitive to caching and things like that. However, the same problem is true on sequential implementations as well.
Yes.
So I don't see this would be any different. I don't believe this efficiency of this. Given we have a large number of patterns, I don't think this algorithm would be any less efficient than you would have on the sequential implementation. So I think it's going to be similar. Multi-core may have a little problem with accessing the database. If the database is huge, they may find the I/O going into the single chip will dominate you, and you will not find it that easy to do. So there are lots of implementation issues here. But in any case, I would claim that that's the end of my homework set for that particular algorithm. I did the best I could. Next homework set. Integer programming, where you can put the word mixed in because you often have a mix of optimization problems which mix integers and non-integers, and the integers are the hard ones because they have to be done by combinatorial search, and the continuous variables can be done by non-combinatorial methods. So you're solving some optimization problems, such as a linear function if you do linear programming, and you have various constraints, equalities and inequalities, and you also have the constraint that the elements are integers. And the non-integer problem, you use either simplex method or interior point method. And the integer problem is used as usually as the challenging one because it's NP complete, whereas the other ones are polynomial time. So that's the problem as posed by Intel. So here is a rather dense slide about parallelization. There is substantial work in the literature on this. I used to work with a fellow called Bob Bixby at Rice University, again with Ken Kennedy on this type of problem. He formed a company called Cplex, which has built a lot of implementations of this type of algorithm. And I know that they sell solutions to the aircraft industry. I mean, that's not the aircraft, the airline industry. So you do not parallelize the linear program solver. Typically, you leave that as a sequential problem. If you look at the linear program solver, it's in principle parallelizable, but it's not very easy because you'll find it has a very high communication over computation ratio, as far as I know, it is not practical to paralyze it efficiently. However, for the integer programming problem, you paralyze what's called, well, I know Bixby always told me it was called branch and cut, but most of the discussion is of the related branch and bound algorithm, which is basically the search, the combinatorial search over the choices, which in this case are integers. But the general algorithm is, the general problem you have is a combinatorial search, where for each choice you have a problem to be solved, which is some sort of minimization problem. So here's the formal algorithm. You take your space, you divide it into a subset into a subspace. You form an upper and lower bound in each subspace, and now we're doing a minimization problem. So if we take a subspace and we find a lower bound for the function in that subspace, or even a value for the function in that subspace, if that lower bound or value is greater than the minimum of the upper bounds from other subspaces I've looked at, we can just remove that subspace completely from the problem. So this is a standard pruning algorithm. So you then prune subspaces. That's why you do upper and lower bounds, because you want, if you can do this lower bound and the lower bound is too high, you can immediately throw away this subspace without actually finding the real value in it. So that's the idea of the bounding algorithm. By bounding, you can throw things away fast. So at the end of looking at this subspace, if it's still active, namely it's not being pruned, and it still doesn't have a value, then you just take the subspace and you divide that subspace up into further subspaces, and you iterate this process. So the parallelism is obvious. It is in some sense data parallelism, because the data, if you like, is these searches. It's parallel over the space of searches. So if you label the search space, it's parallel over that. And it is clearly suitable for thread-based software, because each search is naturally spawned as a thread. Another important feature of all these algorithms is there's usually important shared knowledge. And I will illustrate that in the following slides. And often this is a shared database, and that database just has results from previous subspaces that you can use to make the search and to make the evaluation of a new subspace more efficient. So these problems typically have shared databases, and they also have critical shared numbers, such as the current minimum upper bound. So that's why they're reasonably natural for multicore, because, again, of the shared memory. We have a lot of shared information. And the threading is also natural on multicore.
So also B equals 1 dimensionality for this problem. Anything which is in parallel. So I got the impression that information...
I don't think this one has a lot of communication overhead. This has zero, it has all synchronization overhead. And you see the overheads also is more load balancing, because you will often be searching things, you will find, you'll be doing parallel searches, and then you'll actually prune away that search, because you'll later find one thread might find an upper bound which will render all your analysis of another thread irrelevant. So it's extremely important in these algorithms to search the subspaces in the correct order, so you find the most promising subspaces first, and then you look at the least promising. So this is very clearly illustrated by computer chess, where is a very well-developed area. So this is a particular case of the branch and bound. The space is now the space of all moves. And if we start from we can start from a given position. And if you have a total of n moves, each move has two plies, one ply by black and one ply by white and one ply by black. Roughly at each ply there are 35 legal moves. So this is a tree with branching factor roughly 35. And the space is just the space of the nodes of this tree. And calculating the subspace is now very clear, straightforward in this problem. You go down a tree a certain length, which you think you have enough computer time to do, which is obviously done dynamically, and you evaluate the final, you keep making choices for white and black moves, and then at some stage you evaluate the position you get. Which evaluation has enormous expertise has been poured into that evaluation. It's at the most trivial, queen equals 10, rook equals 5, pawn equals 1, double pawns are bad, owning the center is good, rooks on the 7th rank are good, etc. But it's the greatest, all possible wisdom for just looking at the position is put into that evaluation function, which is a number. If you look at the past, Deep Blue, and which came from Deep Thought, which Deep Blue is famous because it beat Kasparov, probably the world's best chess player ever, and it paralyzed the evaluation function. It had special hardware optimally designed to evaluate this, because it obviously you have 64 by 64, sorry, 8 by 8 board, and you can put some highly optimized special purpose hardware to do that evaluation. And that's what Deep Blue did.
So FPGA.
I don't know what they used at that time. That was, I mean, it was, if you like, the equivalent of FPGA. What exactly they did, I forget. It was done by, this was originally started at CMU as Deep Thought, and then moved to IBM Research, hired the fellow from CMU. IBM Marketing then destroyed Kasparov. Then they shut off the project and the fellow left. Now works, I'm not saying, maybe he works at Microsoft, I don't know. Yeah, he's he wrote a pretty good paper. So just to illustrate this, we had a great failure in this field. We built, although we did do probably the largest parallelization ever done in this problem, and we competed very poorly in the 1987 and 1988 World Computer Chess Championship using a 512-node parallel machine called the N-Cube, which is a distributed memory machine with 0.5 megabyte of memory per node, if I remember rightly, and a Hypercube architecture. All right, so you don't do upper and lower bounds here. You have this minimax, namely, you evaluate a subspace by assuming that white always makes the best move, and then black makes the best move, and so on. And so white always, if the function is defined so the positive is good for white and negative is good for black, white always maximizes f of x, and black always minimizes f of x at their move. We, of course, are approximating here because we are only going to go down a certain length for current hardware. We do not go to the end. We go to, that's why we need an evaluation function. If we went to the end, we would not need to evaluate because it would be a trivial draw or a mate. But given we're going down to a certain level, which is quite high, as we'll see. Always there's been this remarkable fact that computers do not play chess in the same way people do. Because people use pattern recognition and computers use brute force evaluation of the tree. And as far as I know, there has never been any successful work trying to reproduce the way humans do play chess. The obvious way to do it, we put it into the evaluation function, because that's where humans would use pattern recognition. So here's the illustration of the pruning. So here we have white as the green at the top. So maybe that's the initial node. Then we have 4 moves. It could be pawn to king 4, pawn to queen 4, knight to bishop kb3, pawn to king knight 3. Then we have black's moves. So that's white moves, and then there's black's moves. So white maximizes his moves, her moves I should say, and then black minimizes. So here's black's minimal and white's maximal. So if the first move was evaluated by white and got the subspaces, let's say that I've drawn only 3 of the 35 subspaces. If they were 4, 29, and 13, because black is minimizing, we assume that black would choose the approach which gave a score of 4. We then look at the next move of white, where we have 5, -1, and 2 at the next level. Then we would assume black would choose the best move, which would be -1. But once we got to -1 here, we do not need to look here because -1 is less than 4. We know white would never choose that subspace. So in this, and so the dotted lines represent routes down the tree, which we would not get to because we know already that, well, we know already here, once we got to -11 here, because that's smaller than 4, as long as 4 has been discovered already, we know it doesn't matter what these are. We'll never choose this branch of the tree. So this is typical of these search algorithms. You need to find the best answers quickly first, the most plausible, and then you throw away, then as you look down the less likely routes, you throw them away more quickly because you'll find that reasons that they clearly would never be chosen. So this reduces the effective branching ratio from 35 to 6, which makes it a far more effective algorithm. So that's pruning. And the way we parallelized it, which is the only which is bound to be the way you would do it now, but we didn't in detail. We looked at the appropriate points in the tree, and where we had 35 legal nodes, we just divided them between 2 teams of processors. We call them teams because we may do a further division. So we essentially assign them, in this case, the 35 legal moves to 4 threads, and then those threads are spawned off to look at those 35 over 4 moves each, and then as you go down to the tree, you spawn off more and more threads. And even on this distributed memory computer, we found speedups of 100 on a 512 node machine. I assume that speedups these are very suitable for multi-core. You should get extremely good speedups, and you should be possible to build very efficient, powerful search algorithms of this general type.
Has there been any work done with applying annealing to this search? Because this is, a min-max search, right? So annealing might produce better results, wouldn't it?
I'm not aware of it. So the challenge, I think, is to try to make it a little more like people. Right. As far as I know, there is not even an understanding as to how people play chess, which is really remarkable. Yeah. Also, I should say, I often use the internet has very good chess viewing, and there's lots of. I never look at the games played by computers. They're so boring. I only look at games played by people. All right, so you need to have a shared position database in this problem. You need to share those magic scores at the top, these maxima, these counts. But you also need to share you're going to get the same position many times in different routes down the tree, because in chess, transpositions give you the same. You can transpose moves and get exactly the same position. And in a deep tree, that's going to happen continuously. So you wish to reuse earlier evaluations when you're just pursuing a tree which is transposed from the previous tree. So you need to have a hash table storing evaluations to look them up, which, as I pointed out, as far as I know, is a general feature of these branch and bound algorithms. That this is the shared knowledge. The subspaces are not independent, and you can use the results of one search in other searches to speed it up. Even on a distributed memory machine, we actually use the shared database and implemented it in a distributed fashion, and it ran extremely efficiently. But again, multi-core should be particularly good here because it's obviously more natural for shared databases and also natural for fast thread synchronization. So here's some. I mean, if it was true that computer chess was interesting, the trouble is computers are too good now. Here's a PC beat Kramnik, who's the current world champion. Just a PC did. So it's now perceived to be uninteresting. So, but it is clear that the new generation of multi-core chips can do computer chess very well, and that in building something like that, you can build it to be a very powerful engine to do general branch and cut and branch and bound algorithms, which are an important component of the Intel homework set. So I see that as at least an interesting problem area to look at. Notice how deep they go in the tree. This is deep Fritz goes 17 to 18 plies. That's 9 moves deep. 9 moves by black and white deep. So that's quite impressive. They do that by what's happened over the last few years. They just optimize the chess wisdom that's gone into these programs, which is true again in all these search algorithms. By choosing, as you can see, choosing the order of the search and how you do the search can make enormous differences to the efficiency.
Yes, so at a higher level, the parallelism here is to simultaneously evaluating many positions.
That is correct. And that's true of all these. That's the same with the integer programming problem. You have many, this is standard combinatorial search parallelism. Of course, there's the trivial combinatorial search where you just do everything independent. But these are interesting because the searches are not unrelated, and they also get pruned. So you need to have some optimization in the way you do this, so that it would be stupid to do all the implausible ones first, because those you wouldn't prune. And then you would find at the end the good results, which will prune away all your early results. So you must do the good work, the most likely things first, and then you still do the slightly implausible things, but you do them later because you can usually prune them out very quickly then. So that's, and obviously there is a framework. There are many many frameworks I found in the web for this. How many of them actually been used, I don't know. It's obvious you can build general frameworks. But multi-core, I think, suggests slightly different implementations than I suspect people have done in the past. And so really looking at this problem class, I think it would be highly fruitful. And if Intel is correct, it's a reasonably important problem class because integer programming is pretty important. All right. Last problem, last homework set. Support vector machines. All right. So the sort of so I again studied this by using Wikipedia and papers I found on the internet. So the sort of simplest support vector machine problem is you want to find a simple criteria for dividing a space into two. And in the simplest cosmic problem, you have two data sets, and you wish to find a plane that splits the space into two with one data set one side of the plane and the other data set the other side of the plane. And that is the sort of classic problem, and this is called the training problem, which is one of Intel separated the classification, which is using the results, which I assume is actually pretty fast, from the training, which is presumably much slower because it involves a potentially large training set to get the results. So here's some fancy mathematics. We use effectively a least squares minimization principle to find this hyperplane, and it ends up as minimizing a quadratic form subject to a set of either both inequalities and equalities. And the matrix G, which is the thing in the quadratic form, is in its simplest fashion. Yi is actually just plus or minus 1. It just represents the one which just tells you whether the data point I comes from one of the two samples. And the critical thing is this kernel, which in the problem I drew, which was a purely geometrical problem, is just the scalar product of the points. However, you can do all sorts of variants of support vector machines where you replace that kernel by almost anything under the sun, as far as I can see, which just corresponds to not drawing a plane, but a more complex function separating those samples. So, however complicated this is a function of the training set and not of the undetermined variables alpha, and so it's still a quadratic programming problem. So this represents a quadratic programming problem with a dense matrix G calculable from the training set. And n is the number of data points. So this will end up being data parallel over n, or n squared. So obviously to minimize this, I've forgotten whether I'm minimizing or maximizing. Yeah, we're minimizing. Minimizing this, we do the usual thing we do in quadratic programming. We differentiate it, and we get a set of linear equations where we have to solve the g of alpha is on right-hand side. We will use Lagrange multipliers and things like that. And the challenge in this problem is that the solver matrix G could be very large. If the solver matrix G is not large, I don't think the problem is challenging. But in the literature, they were looking at problems which doesn't seem to be implausible, where you had 1 million data points, and so G is the 1 million by 1 million matrix. And so this is totally different from the previous problem, which did not have large matrices. Here we have huge matrices, and we can ask I should say that for this type of problem, usually in quadratic programming, you use conjugate gradient as the solver, because otherwise you get ill-conditioned results with such matrices. And also, conjugate gradient tends to properly search systematically the important directions in the space, because it tends to isolate the directions. It gives you first the directions which where the corresponding to the larger eigenvalues of this matrix G. G is usually positive definite because it's a symmetric matrix, and you look at its construction as positive definite. So there are many papers on parallel SVM, and they basically use two approaches, which I will explore on the next slide. So the first approach, which is to solve the matrix problems in parallel, because these are just matrix problems, and we know how to solve matrix problems in parallel. So you take the full problem, and it turns out that these people claim you cannot solve the full matrix G directly. You have to use some iterative approach solving smaller matrices, and they actually choose around 150 by 150 as the smaller matrix. And I didn't quite understand how they made it. They moved up to the full problem, but then this matrix, which is a 150 by 150 matrix, is then solved in parallel using standard parallel algorithms. So that's the solving the matrix problems in parallel. The next way is, in some sense, simpler. You do not do data parallelism over the matrix. You do data parallelism over the data set. You say, we will solve the SVM problem on n processors, each for 1 over m, by taking the data set and dividing it up into 1 over m processors, when we're putting part on each processor. So this is the same method we use for frequent item set mining. And then we solve multiple subproblems, and then we ingeniously take the results of the subproblems and join them together. This was criticized by the people who wrote the later paper solving the matrix problems in parallel by saying that's fine, but it doesn't solve the same problem. Because it's a different approach to, doesn't technically have the same semantics as the original SVM formulation. I'm not clear to me, as I'm not a worker in this field, whether that's really critical, because the original SVM is full of heuristics. This is not clear exactly which SVM you should use, which kernel K you should use. So it's not so obvious to me that we can't have a few more heuristics, such as how we join the results of different subsets together. And if we also think about this in general, we're going to usually solve a problem, then get some more data and incrementally want to improve the results. So this idea of being able to add data sets together looks quite useful. Now if we look at multicore here, whereas multicore was wonderful for integer programming, it's not quite so clear for SVM. It looks as though it's usable, but the trouble is it doesn't address the huge size of the matrix. Because multicore almost by definition has a standard memory on the chip and doesn't give you lots of extra memory, whereas the current formulations are dominated by the size of this matrix G. So there are two problems. We can do any of the parallel algorithms we've looked at appear to work fine on distributed memory machines, and they also have the advantage on distributed memory machines we get more memory. We get more DRAM because we get DRAM on each CPU in our distributed memory system. So I would say this needs some more research. It's not so obvious. In a trivial sense, it's obvious how to use multicore, but I'm not certain how good it will be because we have not addressed the large size of the matrix G. And here's some results on an IBM. This is from the people who parallelized the matrices. There are their names there. It has this paper called Parallel Software for Training Large-Scale Support Vector Machines on Multiprocessor Systems. Has reasonable good discussion of previous work and references there too. And here are 4 test problems. Here's linear speed up, and here's the results. On one of the problems, they get superlinear speed up, namely a speed up greater than the number of processors, which is often happens when you have large problems, because you get better use. You get more cache in a multiprocessor system than you do in a single processor system. So superlinear speed up is often seen. I don't think it means anything very deep. It just means that when you put in the effects of cache, sometimes multiprocessors look better than two single processors. So I would say SVM is suddenly we can tick it off as we know roughly what to do. I doubt if the last word has been said here. That was the end of the homework set. Are there any questions on the homework set?
So you think Intel will provide, since Intel put SVM as one of the applications there, they probably will have library to eventually develop.
I don't know whether Intel writes software. I thought Microsoft wrote software.
No, there's MKL and IGP. They have FFTs and some version of Glass.
So,
Yeah, so I mean, Intel obviously has some basic thing. Whether they are systematically developing the software for their multi-core challenge application set, I have no idea, because that comes from the application part of Intel, not from the software part of Intel.
They just updated their FFTs last November and got a 4 to 6x speed up on their multi-core scenarios. Insane.
Yeah, well, FFTs are a lot better understood. FFT is a lot better understood than these algorithms. FFTs, we've known how to, the optimal FFT algorithm's been known for a long time. As I mentioned, FFT, I don't know what they did, but FFTs on multi-core should have many obvious performance improvements due to these transposition possibilities. They should run very well on multi-core, in my opinion.
Well, we're dealing with them on GPUs now, which are 128 core, and they use a totally different algorithm. that doesn't do the transpose, and they get another factor of 2 to 4 over this, about a factor of 4 over the CPU.
But yesterday you said that FFT is very hard to parallelize.
Well, it's hard in the following sense. The overheads, the communication overheads on FFTs are higher than on other algorithms because of the, if you like, partly just the low CPU count, because we have a logarithmic algorithm. It's n log n. The order n squared version of the FFT is super easy and it has super efficiency. It's of dimension 1. As I mentioned in my analysis, the FFT fast Fourier transform is dimension infinity. It's got, because it is not, the overheads do not formally go like 1 over the grain size to a square root as in 2 dimensions. They go 1 over the log of the grain size. They do not go down very fast. So getting good performance on FFTs is challenging more challenging than most other traditional data parallel algorithms, such as solving such as matrices. All right. So anyway, I would claim that as a result of the homework set, we would see so far no challenge. We think it looks as though most, if not, I mean, I try to look at the Intel application suite which were not clearly extrapolable from existing data parallel algorithms, and I try to show that at least we had a beginning of an approach to all those ones we looked at. Whether that's, so I would say, at least if you believe the Intel application analysis, that's reasonably promising. All right. So we now go back to the original discussion. All these slides are on the web. I gave the link at the first lecture. And I update them, so these are update. Each day as you saw me giving more homework, I update them. So you should take the latest version. All right, so we go back to the systematic discussion. And what I have here is a systematic discussion of applications followed by a systematic discussion of software. Maybe today we can do the systematic discussion of applications. All right. So we come back to a picture we've seen many times before. That I pointed out that we could think of as programming, as always, as mapping a complex system representing the application to a complex system representing the computer. And we had this so-called SpaceTime picture where both the computer and the application had some sort of data space and some sort of time attached to it, and that the challenge with sequential programming languages is that they map the spatial dependence of the application into time or sequencing on the computer in a way that we could not undo that map so that we could get actual parallelism automatically. So the basic thing that we're doing is taking this application. Here I've got some little green points here, green things here, just representing internal degrees of freedom of the application. We divide it into 4 parts, which we're going to put on 4 processors of a parallel machine. And then the parallel machine is going to get the parallelism, shown by these colors here, but these internal parts will be mapped into time on the parallel machine. So as I noted that the leftover parallelism has to be mapped onto computer time in this mapping. So there are 2, historically, we always talked about two types of data parallel applications. And I used to call them synchronous and loosely synchronous. Historically, we had things called SIMD computers. The most famous of these was the thinking machines CM2 and CM1. They were the ones with the nicest lights which blinked at you. And they had 32,000 processors on each on a full machine, and well, maybe it was 6, but I think it was 32,000. And each of those CPUs ran identical instruction sets. So a synchronous problem is one where the algorithm is such that each data point has the same, can be executed with an instruction set which is an identical instruction set on all data points. So if you look at Laplace's example, the one I went through, that is a synchronous problem. Every data point has exactly the same algorithm applied to it. Most full matrix algorithms are synchronous. And there were, if you look again, and we were talking about the history, 25 years ago, or wherever it was, people at some stage thought SIMD machines were very important. And some people consider GPUs SIMD, but they're probably not SIMD. They're probably, I don't know whether they're SIMD or MIMD. You can tell me about that. Yeah, so that's what I would guess, yes. I mean, so on a SIMD machine, there was never any synchronization problem because everything is running the same instruction set, so you could never get out of you could never have a synchronization problem. So those are synchronous problems. So synchronous problems were historically important because the first science problems looked at were all synchronous. However, as science evolved, synchronous problems became less exciting because as soon as we put heterogeneity into the problem, we found that it was not possible to evolve each data point with the same algorithm. So let's now look at so we can run synchronous problems on a so-called MIMD machine where we have separate instruction sets. And so we can ask, how are those machines synchronized? And the answer to that is they are synchronized by the messaging that you do in those problems. And you do not have to have any synchronization primitives on such parallel machines because it doesn't matter whether the machines get out of time. I mean, they run in different time sequence. There's a load balancing issue, but there's no correctness issues if the machines run in different time with different loads and finish early. Because if they finish early and they wait for a message, they will just wait for the message from the machine that's slow. So they just wait for the synchronization point. So messaging automatically synchronizes standard parallel machines, whether they be multi-core or distributed. And that just says that if I do a send and then another processor does a receive, that act automatically synchronizes. That may be trivial to you now. When parallel computing started, that was not well understood. People thought that there was some miracle needed to synchronize. And the synchronization, there would not be synchronization on large machines, but even on huge machines, this messaging was synchronized with very high efficiency. All you need to do is to load balance to make certain that each processor does the same amount of work to within 10% or something, and then the synchronization will guarantee will work just fine. Because the synchronization is local, you do not get any buildup of overhead or lack of synchronization. So in MPI or any standard messaging system, you just the act of putting a call to the MPI routine synchronizes the process. That's all you have to do. Nothing more is needed. And this says, as I've mentioned, that this is the structure of all these data parallel algorithms. You do an initial, there's some communication which has to be arranged to be deadlock free, which for this so-called shift is done by doing it in 2 steps. You do a communication so that the processors, each processor has enough information to do the next step of the simulation. Then you do a simulation, then you exchange information, you do a simulation exchange, simulation exchange. So that is the structure of all such data parallel algorithms. So I would claim that the most common science and engineering problem is what I used to call loosely synchronous. I don't think many people use that term, but I think it's a reasonably good term. And it differs solely from the previous discussion in that I try to use some mottled colors here to say that we're doing problems now where we still have data points, but now the algorithm at each of these data points in each processor is just different. It could be totally different. I mentioned the Hadrian's Wall. We could have gargoyles in the world. Well, the gargoyles would have a different algorithm from the bricks. So loosely synchronous problems are still doing problems where we have natural problem-specific synchronization, either because we're simulating in time or doing an iteration, but there is no constraint that the algorithm on each point of the application space bears any resemblance to the algorithm at another point. It's usually related, but it doesn't have to have any correlation in computational complexity or what have you. And so I call this loosely synchronous because for the synchronous problem like Laplace's equation, synchronization can be done in this trivial fashion using SIMD machines. In this case here, you effectively have to use machines with separate instruction sets for each parallel component, but the synchronization is still done in exactly the same way. It's done by messaging, and it works in exactly the same way. As far as messaging is concerned, it doesn't matter whether we're using synchronous or loosely synchronous. So these are very old. So here's a heterogeneous problem, just flow over an airfoil, and just the nature of these of such a complex irregular geometry will give you make this problem loosely synchronous. And this is incredibly loosely synchronous, some cosmological simulation, because if you did this problem in any sensible fashion, the stars here would have orders of magnitude less work to do to simulate than the stars here, because the stars here are interacting with lots of other close stars. So the amount of work per data point varies by huge factors for this type of problem. And that makes these problems highly loosely synchronous. And you happen to use things called multiple methods to do this in an optimal fashion. And they're quite complicated to do, but they have exactly the structure of all these other problems. All right, so those are synchronous and loosely synchronous. So we've already discussed asynchronous problems, and so that the computer chess and integer programming will be an example of what I call an asynchronous problem. And here we do not have this universal synchronization like we do in the those synchronous and loosely synchronous problems. However, the feature of the applications, in this case the minimax scores, which provide a set of dynamic synchronization points, that allows you to, I believe, as at least our experiments showed, produce very efficient algorithms. But you would need different types of runtime because you need good threading and things like that. The most extreme type of asynchronous application is the trivial one, tried to represent it here by Tetris, of just packing independent jobs onto a computer. So that's, if you like, another example of that type of problem, where there's no synchronization needed, because the jobs are independent. So that's that type of application. We've done computer chess.
Yeah, so the problem is that if there's no synchronization inherent in the application, then the communication becomes more difficult. So
yes, so I would say, what do? We use, like we did in computer chess, which I claim generalizes to integer programming, we use features of the application to make it run well. I told you the general problem does not paralyze. Grid sphere, that horrible spaghetti Java I showed you, does not paralyze. Computer chess and integer programming will paralyze because of the structure of the application. We have a systematic way of looking at the application and spawning the threads and pruning the threads, which can be implemented with high efficiency. Again, it requires the Marine Corps at least to do the basic runtime. Possibly we can abstract this to say, well, here the non-Marine Corps, you just define your shared database, you define your optimal ordering of subspaces, and you too can program those applications. But to write the core software to make that run efficiently needs great expertise, just as you would do for the GPUs. This is currently all parallel programming is done by experts doing the core algorithms, I would claim. I do not claim to, I told you, I do not claim to paralyze all problems. I do claim, so far I have not found we have the famous examples like Microsoft Word, which was not so obvious how to paralyze. But if you take the class of problems we looked at, which are naturally large because something is big in them, which is sort of naturally parallel, which we found in computer chess, we found in support vector machines, we found in Kmeans, we found in PDEs, particle matrices. These all have something natural in them. And then I claim that there are sort of these classes of synchronization. Synchronous and loosely synchronous are supported by natural messaging. The threading of the asynchronous is not supported by that same type of messaging, because we need to have a different type of way of getting these proper pruning and the proper synchronization on the minimax score. And we also have the shared database. But these are all, they all have a rather clear structure. And so that we're just trying to identify, look at successes, and then try to generalize that success to say, this is the class of applications we can do. That's the approach I'm taking, which I believe is quite successful. All right, so there is this famous thing which I mentioned DoD has wasted a few $1 billion on, called discrete event simulations. And discrete event simulations correspond to thinking about a problem as a set of entities, which entities send messages which are timestamp messages saying, here is an event, it is going from me to a certain set of other objects, and this message has a timestamp, which is a simulation timestamp. Please act on it according to that simulation timestamp. And this is often applied in war games. It's also implied in some chip simulations. And if you want to understand why it's used, if you look at the world, I notice the world, if you look at it in terms of the fundamental quantum chromodynamics, is probably synchronous. We can simulate Microsoft from QCD in terms of a synchronous algorithm, but it would be rather difficult because there are a lot of particles inside Microsoft people and things. So instead of which, so at the most fundamental level, nature is synchronous. If we look at it in terms of particles and mesh points, it's actually loosely synchronous because we're abstracting nature in terms of concepts such as grid points and particles. And now what DoD does when it tries to win the battle or simulate the battle, it actually thinks about it in even coarser grained fashion as tanks, nuclear bombs, and bullets and ships and things like that. And that's where you get discrete event simulations. It's no longer loosely synchronous because it is not natural to step these things in time, because at this level of macroscopic description, it is not natural to have the same time sequencing for all these different macroscopic objects. So this discrete event simulation is hard to parallelize because there is a global simulation time. And you are only allowed in principle to actually execute the next event in simulation time. However, you don't actually know what that next event is because here so you take the event with lower simulation time and you execute it. Maybe it generates another event with an almost equally low simulation time, which is the other one you have to simulate. So these are in general impossible to discrete event simulation in general is impossible to do in parallel. There's some famous work on conservative and optimistic simulation in this area. In the optimistic simulation methodology, you take all these objects, and here we were simulating a well-known battle in 1066, the Battle of Hastings, where poor old Harold lost his life. But you would simulate each of these things here, the archers and the pikemen and Harold, in time, on their own time, and then if an event comes, such as an arrow that pierces Harold's eye and kills him, and you would actually simulate Harold further in time, you would roll back Harold to the time he died. And if Harold had done something like issued some orders, you'd have to roll back those orders and things like that. So the optimistic approach to discrete event simulation is rather similar to software transactional memory. You're rolling, you do speculative execution, and so obviously this works if this particular problem is almost a classic simulation problem, and the discrete event just gives you a little extra. And so it runs pretty well, and you don't have to roll back very much. However, the field is not terribly healthy. The funding is quite low. DIMSO, the Defense Modeling and Simulation Office, doesn't seem to be doing so well these days. And I would point out that Multicore is very good for this problem because at least we can process these event queues and find the global simulation time and propagate it quickly to different cores much better than on distributed memory machines. So I would say that the jury is out on this, but it's not even quite obvious this is a good simulation model, because notice you only get this model if you make approximations. Typically you're simulating things which are actually loosely synchronous, but you're just making approximations to them for efficiency, which gives you the discrete event paradigm.
We've seen cases where people have discretized this back at a finer granularity, solved it sort of with a continuum mechanism for how these guys maneuver, and then achieve speedups.
But that's sort of what I'm saying here.
Yeah.
As you go with discrete event simulation, as you go to a finer resolution, you'll find that the discrete event simulation is actually not a discrete event simulation. The discrete event part comes because of this macroscopic view you're taking, which is taken for a seemingly efficiency. The trouble is the efficiency is only an efficiency on a sequential machine. On any parallel machine, this is a highly inefficient way of thinking about it.
So why doesn't this work more like chess? I mean, couldn't I?
Because you don't. Chess doesn't.
Different possible outcomes for a given scenario and speculate massively and get a 35-way tree and use the same.
Well, you would use that. So this would have a similar runtime as computer chess. The problem is that this doesn't have such a simple. Computer chess has a very clear minimax principle, which allows you probably to do the speculative execution in a highly efficient fashion. In general, discrete event simulations do not have that feature. I mean, I say Harold does not know an arrow is about to pierce his eye. And poor old Harold could have done an awful lot of things before this arrow appeared. So it is not easy to do this. Whereas computer chess, we understand such a lot about the structure of the problem that we can arrange the threads so that we do not waste too much time. I consider this reasonably I'm not trying to be negative. I would view this as a promising area to relook at, because multicore is obviously a good architecture for this.
Question?
Yes.
Your comment that this is sort of a transactional memory would be useful here. I guess it's only for recovering from incorrect events. I'm thinking that speculative parallelization may be a better fit for this, because in reality, events happen in a deterministic sequence. I suppose transaction memory actually just ensure it's consistent, right? It doesn't care whether it's this sequence or that sequence as long as it's linearizable, for example.
But I didn't say it was the same as transactional memory. I said it was related to transactional memory. They both have the idea that we are going to reconstruct. We're going to allow incorrect things to happen and then roll back to the thing.
Parallelization also allows.
Yeah, well, I would say this is optimistic discrete event simulation is speculative parallelism. And I should say that problems DoD had was probably not due to the paradigm. It was because DoD started this work a long time ago when nothing existed, and they built up a huge infrastructure which has everything in it, including the equivalent of Corba. It's all built into DoD systems because they built everything from scratch, from the object model through everything. And then they should the trouble is the field is now very weak and doesn't have any funding. They should, in my opinion, I think redoing discrete event simulation using only putting into this, I should say one lesson I have looking at all this field is we have bundled too much into most software. We need to abstract a few simple things and just do that simple thing very well. And we should redo discrete event simulations only doing what's called time management well, which is the handling of the global time and the optimistic simulation. We should not do all this object junk which they did, because object junk has been done better by other people. We should try to take these key ideas and only do one idea at a time and do it extremely well. If we try to package too many things together, we'll die, in my opinion. But it's an important class, it's in principle an important application class, which is of interest, I think, for multicore. All right, here's another class of problem, which is this I've mentioned many times. This is the meta problem class. And the fine-grained data flow is actually sort of the programming model we looked at for computer chess. The coarse-grained data flow is, again, I mentioned, it's the thing where you take in the case of, say, aerospace, you take the different components of designing an aircraft and join them together to design a complete aircraft, which is often of importance to do between companies, because the company that builds the wing is different from the company that builds the engine and so on. We do ocean, land, and atmospheric. I would say this was originally, in my opinion, first well understood in a piece of software called AVS from the visualization area, where there's a whole set of software that came out that supported the ability to take image processing and visualization algorithms and join them together with nice arrows, and they were highly successful. And this is now called workflow or mashups in the real world. And I try to say, I would view everything I said up to now. You now add data flow and composition, and you get meta problems out of sub problems, where each of these things here, like structural analysis, acoustic simulation, those are data parallel or loosely synchronous. The optimization could be this integer programming fine scale. So the model I would have is the data flow, coarse-grained data flow is your cosmic wrapper. Then that wraps the little components, and each of those components are these finer grain size, more powerful, more larger scale parallelism type applications. But yes.
Here, talking about web service, right? It's a very different architecture. You get many different servers, like server farm.
Yeah, but I would say it shouldn't be different. As far as I can see,
The concept should be the same.
yeah, because what do you need to make a web service work? Well, you need to have, you need to make certain you don't care about many milliseconds of delay and things like that. So I would say that coarse-grained, as far as I know, all the coarse-grained data flow I know in science can be done perfectly well with web services and workflow. And they were used to be done with different technologies. I think all the things you do with AVS can be done with this type of workflow technology, because all that's required, I'm not trying to tell you which is the certain piece of software is better than another piece of software, but the concept, the application structure is of coarse-grained objects, which actual objects might themselves be parallel, and that you link those software together by data flowing between them. That's data flow. And here's some standard workflow. And then mashup, as far as I know, workflow in web service world is the same as mashups in the real world. I don't see any difference. You look at the pictures, they look the same. And there are lots of tools here. There's one called Proto which is a standard. You can see a nice visual interface here. They're the same. These are the same type of tools as AVS and things like that. They're just getting reinvented with a different name, but with a different core technology. So one reason I'd like to try to do one thing as well, as far as I can see, mashups and workflows and coarse-grained meta problems, they're going to be fought out in one space, and we should just smile and let that space decide how to do it well. And then we'll take these components and do data parallel separately, and then we'll plug it into this, whatever wins in this world. We don't have to worry about which wins. But what we shouldn't do is try to put everything together, because we're bound to, in this world of rapidly changing technology, we're bound to lose out if we put too much together. So you asked me about MapReduce. So I would claim MapReduce is a data flow with data parallel components. So I looked that up for you. And although it doesn't use the word services, as far as I can see, you can consider what they do in MapReduce as services. And the services they seem to discuss are document-related services, and they also do automatic data parallelism for the services which are the standard. Here they have an example of counting words in a document. They happen to like Lisp or something, so that's a language. I don't really care what language one uses. That's again some battle one should let the world fight. So this is I would say, a nice, elegant example of data of the coarse-grained meta problem implemented as a set of components where each of these components is a data parallel component, here emphasizing documents. And there are many other examples of that. And this is a very important problem class, and it includes, as I said, the same science problem class where I have ocean simulation joined to atmosphere simulation, or acoustic joined to wing joined to engine. These are all these meta problems. So this is a meta problem. And it's now 12 o'clock. So next time we will finally get to this analysis of software systems. So this is roughly the finish of my analysis. I tried to go through the homework set, and then in this last part of this lecture, I went through these broad classes of algorithms. So the meta problems, the discrete event simulation, the fine-grained functional, the loosely synchronous, and the synchronous. And those, I claim, are the critical problem classes you need to support for parallel computing. And as far as I know, all problems fit into these classes. And therefore the software, which we will discuss, better support these classes or decide it's not going to support it because some other piece of software will support it.
Well, thank you for the presentation today.